Hello, today we are going to learn trails, paths, and circuits. This is in chapter 10 of the textbook. The chapter 10 is Theory of Graphs and Trees. Chapter 10 has 6 sections. We're going to learn all the 6 sections in Discrete Math 2. Today we are going to learn the first section, which is trails, paths, and circuits. This is a long section. Because of that reason, I split the section into 2 parts. Today I teach the first part, and the next part will be taught in the next class. All right. So these are very important concepts: trails, paths, and circuits. All right. Before going to more details, let me explain a real life story. Graphs, the graph theory or the graphs are discovered long before. Nowadays, people are using network tools for computer science. It is very recent. But the concepts of graphs or the concept of networks existed long before. So this is a story about that. Let me read the description here, and then I will stop when I want to explain a little bit more. This The subject of graph theory began in the year 1736, when the great mathematician Leonhard Euler published a paper giving the solution to the following puzzle. Okay, so this is the mathematician who's called Leonhard Euler. He is known as the father of graph theory or networks. This story explains about a puzzle. Let me explain this a little bit more. The town of Königsberg in Prussia. All right, these are old names. Prussia is called Russia now. Prussia is called Russia. And then Königsberg is called Kaliningrad in nowadays. So those are the 2 new names for the city and the country. You know Russia, and sometimes you might know this city. The interesting thing about this city is there are 2 branches of the river Prigel came together at this city. So there's a city and there's a river. This river is making a nice structure. Okay, so this is a map of the city. Okay, this is a map of the city. So this one shows the corresponding the river. All right, so river is given here, and there are bridges. So these are the small line segments are the bridges. Okay, they are the bridges. Okay, so these are the parts of the city. A here, A there, B, another part of the city, another part of the city, and then here D, and finally C. Okay. So in the next slide, I say it consisted of an island connected by 7 bridges, as shown in figure 10.1.1. All right. So these are the 7 bridges. So one bridge here. Let me mark another bridge here. Okay, so these are the 7 bridges. there are 7 bridges, and then as I showed you before, there are parts of the city there. This river divide the city into 4 land masses. Okay, this divides, the river divides the city into 4 land masses. So these are the land masses I showed you before. All right, so go forward. So this is the question. This was an ancient question, but they couldn't find a solution for this. All right, so this is very old question that they couldn't find the solution. Finally, Euler came and solved the problem. All right, so can you remember the mathematician's name? Leonhard Euler. And he came and solved the problem. Okay, so let me learn the let me explain the problem. Is it possible for a person to take a walk around the town, starting and ending at the same location and crossing each of the 7 bridges exactly once? Okay, so this is the problem. I'm going to read the problem again. Is it possible for a person to take a walk around the town, starting and ending at the same location and crossing each of the 7 bridges exactly once? All right, so this is the problem. So you have to start from one place. Let's say you are starting from here, and then you have to visit all the parts of the city. That means you have to go from A, you have to go to B, C, D, and everywhere, and then come back to A. There's more restrictions. That restriction is crossing each of the 7 bridges exactly once. Okay, crossing each of the 7 bridges exactly once. Okay, and then start and end at the same location. There's another constraint. Okay, so these are the 2 constraints. Okay, so constraint number 1, constraint number 2. All right, so you have to walk around the city with these 2 constraints. To solve this puzzle, Euler translated it into a graph theory problem. Okay, as long as this problem, like a real life problem, finding solutions might be really hard. So then what Euler thought to convert this one into a graph theory problem to make it convincing. All right. So now he's trying to turn this into a graph theory problem. If a person can travel within a land mass without crossing a bridge, he marks such land masses uniquely. Okay, so that's clear. So let me explain it again. If a person can travel within a land mass without crossing a bridge, he marks such land mass uniquely. That means let's say you are starting from first of all, let me highlight the river. So let me use a different color, blue. I will use blue to highlight the river. I'm not blue, I will use a different color. This. All right, so this is the river. No, it's not visible. Let me use a different color, maybe this color. And then quickly I will mark the bridges. So this is the land mass. the bridges and the river. So this explains if a person can travel within a land mass without crossing the bridge, he marks such land mass uniquely. That means, let's say you start from here. All right, you start from here. You can go anywhere in this part without crossing a bridge. All right, you can go anywhere in this area without crossing a bridge. So in that case, he marked that land mass with a unique symbol. That means A. He marked that land mass uniquely. So in that case, this entire part is A. And then go to the next part. Let's say he's here now. He can go to anywhere in this area without crossing a bridge. So he marked that as a different letter, which is D. And then this as C, that as B. All right, so those are the land masses. He found 4 land masses. That's marked right here. All right, so let's go to the next slide. To solve the puzzle, the Markov-Konigsberg can be identified with the graph figure 10.1.2, in which the vertices A, B, C, and D represent land masses and the 7 edges represent the 7 bridges. Okay, now we are going to put this into a graph. Let me mark these land masses as vertices. So I have vertex A, here, the landmass A is marked with a vertex, and landmass B and landmass C, and finally landmass D. Okay, there are 4 land masses. Those 4 land masses are marked with vertices. All right, now if there's a bridge between these 2 land masses, one of the 2 land masses, then you have to mark an edge, okay, which is given here. All right, so let me check that. You can consider this and that 2 land masses. There are 2 bridges in between A and B, right? Between A and B, there are 2 bridges. So you mark 2 bridges with 2 edges. And then if you consider A and C, yes, between A and C, there's one bridge, so you could mark that like this. And then between B and C, there's one bridge, B and C. And then between D and C, there's again one bridge. And then no bridge between A and D. Okay, no bridge between A and D, no bridge between these 2 land masses. And then I think this is the corresponding graph. Okay, let me just restructure this graph, because the way the graph presented here, it is not clear. So let me just change vertex D and vertex C. Let me interchange them so I can draw a clear graph. So what I'm going to do, I'm gonna mark C here, D there. Okay, then there's an edge there are 2 edges between A and B, and 2 edges between B and D. And then from here to there, from here to there, and from here to there. Now it's clear. Okay, so this is the graph we have. All right. So let me read the problem again. The problem is this: is it possible for a person to take a walk around the city, starting and ending at the same location and crossing each of the 7 bridges exactly once? Okay, so let me consider. I'm starting from here. Okay, I have to come back to the same place. I'm starting from here, and I have to visit all the cities. That means all the areas. That means all the vertices, and I have to cross um, each bridge exactly once. So you could go like this, come here, and then you could go like this and come here, and then you could go like this. All right, once you go this way, you won't be able to go that way. The reason for that is if you go that way, you have to cross either that bridge or this bridge or this bridge. That means you are just crossing those 3 bridges, one of those 3 bridges in the second time. So you are not allowed to cross any bridge 2 times. That means you will not be able to go that way. Okay, so you will not be able to go that way. Let me take that out. And then from here you could go upward to the same point, and then from here you could go to that place. Okay, this is one possibility, but in this possibility you can see you couldn't cross that bridge and you couldn't cross that bridge. Okay, so you can see that this path does not cross each bridge, so this is not a solution. So like that you can try several solutions. Okay, let me try some other possibility. Okay, let's say you are starting from here, from that place, and then you are going that way, comes here, and then you are going that way, comes here. Thereafter you can go that way. You can go that way, because if you go that way, then you have to go that way, and then that just stuck you right here. Okay, you won't be able to go back to C. All right, so you are here now, and then you might think of going up. All right, and then you might think of going down, and then like this. You started from C and came to C, but the problem is you couldn't go through that edge. So that means you couldn't cross all the bridges. Okay, so that's also not a solution. Like that, you can try several solutions. Okay, you can try several solutions. Unfortunately, this problem doesn't have a solution. So the answer is no. You won't be able to do that. Okay, you can just start from one landmass and come to the same landmass while visiting all the other land masses and crossing each bridge exactly at once. That is impossible. Okay, so the answer is no. So you could get the answer easily once you have this graph. Okay, so that is the meaning of graphs. The graphs are very helpful, okay, to understand this dynamics. All right, so that is the Konigsberg problem, the famous Konigsberg problem, which is from 18th century. Now we are going to learn some technical terms. These technical terms are very important. Let's read one by one. Let G be a graph and V and W be vertices in G. Okay, G is a graph and these are vertices. All right, so then we are going to learn some definitions. A walk from V to W is a finite alternating sequence of adjacent vertices and edges of G. Okay, now this is called a walk. Okay, so this is the definition for a walk. So you can have finite alternating sequence of adjacent vertices and edges. Okay, that is called a walk. All right. As an example, let's say you have these vertices and these edges. Okay, you can define a walk like this. You start from here and go that way, go down that way. Sorry, and go that way. Okay, this is called a walk. Let's say this is V1, V2, V3, V4. So this walk can be given by V1 to V2 to V4 to V3. Okay, if you need, you can just come back. V3 to V2. I'm sorry. And V2 to again V4. Again going down. Okay, so this is walk. Walk is any finite sequence of adjacent vertices and edges. All right, so let me read the rest. Here, this is the general form of a walk. It has the starting vertex, next edge to be crossed, vertex, edge, like that. All right. Then it ends at a vertex. All right. Where V's represent vertices and E's represent edges. All right. Then you take the start as just V and Vn as W. So those are just notations. You take V, the starting vertex as V, the ending vertex as W. All right. So this is just the definition of a walk. Okay. Then we are learning about trivial walk. Okay. You know the word trivial, that is used in mathematics in lot of times. Trivial means the simplest case that is exist. All right. Now just consider trivial walk. That's the simplest walk that could exist. All right. So this is about a walk. This is about a walk, and then trivial walk. Trivial walk, the simplest case that can exist. That is just a edge. Just a vertex. Okay, just a vertex is a trivial case. That means you don't have any edges. That means you start from this place and just stay in the same place. V1. That's called a trivial walk. All right. Good. And then we are going to learn. I'm sorry. This is a trivial walk. The trivial walk consists single vertex, and then we're going to learn trail. Trail is a walk from V to W that does not contain repeated edges. Okay, so it's a trail is a walk. Walk is a sequence of edges and vertices, but especially what happened here is it does not contain repeated edges. Okay, that is very important. It does not contain repeated edges. All right, that means something like this. This is a trail. That means let's consider this the same. Just consider the same graph. This is V1, V2, V3, V4. All right, so then I'm gonna write a trail. You're starting from here, maybe, and going that way, and going this way, and going that way, and you could go this way. That's it. Okay, you won't be able to cross the same edge. All right, let me draw something else. Let's say you are given this, that way, this way, and this way. Okay, so is this a trail? No, this is not a trail. Why? Because this edge is repeated twice. Okay, that edge is repeated twice. So you are going like that, 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 that. Okay, this is not a trail. Let me draw the trail again. So the trail that we are interested in is something like this. Go like that, go like that, maybe go like that, go like that. Stop there. Okay, let me write it. It goes like V1 to V2 to V3 to V4 to V2. Okay, no repeated edges. That's a trail. And then we're going to learn path. All right. Path is a trail that does not contain repeated vertices. No, path has more restrictions. That means you can repeat vertices too. Not only edges, you can repeat vertices too. So let me draw that one here. Let's say this is V1, V2, V3, V4. Like this. All right, now you could go like that. You could go like this, down like that. And then you could go like that. All right. And then you can come back like that. You are not allowed to do that, because if you do that, this vertex is repeated. Okay, that vertex is repeated. So that is not a path. So let me edit it. This is of course a path. Keep that as the path. Okay, so this is the way you move. The dynamic is like this: V1 to V2 to V3 to V4. Okay, so that's the dynamics. All right, now go to a closed walk. Walk that starts and ends at the same vertex. It's a walk. Okay, we learn walks here. Closed walk is something very simple. It's a sequence of vertices and edges, but start and end should be the same. Okay, start and end should be the same. Let me draw something here. Closed walk. All right, let me draw the same graph. V1, V2, V3, V4. All right, this is a close walk. You could mark the close walk like this. and then you go up, and then come back to the same place. All right, now let me write this. This goes like V1 to V2 to V3 to V4 to V2 to V1. So you're coming back to the same place. That is called closed walk. Okay, then I don't have enough space. Okay, I can go down. And then I'm gonna talk about circuits. A circuit is a closed walk that contains at least one edge. So closed walk that contains at least one edge that does not contain a repeated edge. Okay, so there are some qualities that you have to satisfy. It's a closed walk, keep that in mind, that should contain at least one edge, that's the second condition, and does not contain repeated edges. There are three conditions you have to satisfy. Okay, let me draw the case here. It's a circuit. Okay, so this is an edge, vertex, 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 vertex. 1, 2, 3, 4. From here to there, there to there, there to there. Alright, so now it should be a closed walk. That means you start and end at the same vertex and contains at least one edge, does not contain repeated edges. Okay, so you could think something like this, like that, and like this. Okay, so you could think like that. All right, so let me write it down. This is from V1 to V2 to V4 to V1. We start and end at the same vertex, but no repeated edges, contains at least one edge. Now go to simple circuits. Okay, simple circuit is a circuit that does not have any other repeated vertex except the first and last. All right, it's a circuit. That means when you say circuit, that means it doesn't have repeated edges. See, it doesn't have repeated edges. So it's a circuit. Other than being a circuit, it should not have repeated vertices too. Okay. You can just have the first and last vertex as common, but that's it. No more common vertices. Okay, this is a simple circuit. From here to there, there to there, there to there. V1, V2, V3, V4. No repeated edges and repeated vertices, but you could repeat the first and last vertex. Go like that, go like that, go like that, go like this. So this is a simple circuit. By the way, I'm thinking of changing this little bit. Because this is a circuit at the same time that's a simple circuit too. Okay, so how do I change it? It is hard to change, so I have to change the structure here actually. Make it like this. Let me put another edge. Okay, now the problem is complicated. So now I can mark a circuit, which is not a simple circuit. So I'm going to explain the issue here. So this is a circuit, of course. This is a circuit. Rather being a circuit, this is a simple circuit too. This is a simple circuit too. So I want to distinguish this and that. I just want to distinguish this and that. So because of that reason, I'm gonna change this network. Okay, so I added one edge. All right. Now let me draw it again. Here you start and end at the same place, and you can repeat edges. You could go like that. You could go like that. And you could go like that. You could go like that. Oh yeah, this is good. That's good. So it repeats vertices but no edges. Okay, so let me rewrite this. Now this is a circuit which is not a simple circuit. It goes like V1, V2. Let me mark this as V5. V5, V3, V1, V2, V5, V3, V4, and then V5 again, and then V2, and finally V1. Okay, which is a circuit but not a simple circuit. Okay, so now just let me finish this. This is V1 to V2 to V3 to V4 to V1. Alright, now you understand everything. So here we discuss one example for each. We learn about walks, trails, paths, closed walks, circuits, and simple circuits. Alright, so this table summarizes everything. If it's a walk, repeated edges allowed, repeated vertices allowed, start and end at the same point allowed, must contain at least one edge, no. And if it's a trail, then repeated edges, no. Repeated vertices allowed, start and end point at the same point, allowed. And must contain at least one edge, no. Okay, so this table summarizes everything. So you can read this table. Now let me go to the next slide. This is an example we have. Let me read this example. So in this example, we talk about notation for walks. There can be several notations you could think of. So it is not unique. That means the way of giving a walk is not unique. So you can just use vertices, or you can just use edges to represent a walk, or maybe edges and vertices both. Okay, it is not you. But what you have to make sure it is not an it is not unambiguous. Okay, so let me explain this slide. The notation E1, E2, E4, E3. The notation E1, E2, E4, E3 refers unambiguously to the following work. Alright, so the same work, this equals that. E1, E2, that means E1, E2, E4, and E3. Right, go like that. Starting from here, end at that. All right. At the same time, you could use vertices also to represent. That means V1, V1, E1, V1, E1, V2, E2, V2, E2, V3, E4, V3, E4, V3, E3, V3, E3, and then V2. All right. So both are correct. Either you could use. Give me a second. Either you could use this simple notation, or you could use this long representation. This short representation or the long representation. As long as it's unambiguous, that's fine. Okay, so that's what I'm explaining here. What I want to explain is the representation is not unique. The notation E1 in the above figure is ambiguous if used by itself to refer to a work. It could mean either V1, E1, V2 or V2, E1, V1. That's what is explained here is, let's say you are just representing E1. You just represent E1 to denote a path, just E1. Okay, I'm going to use the different color. Just maybe this is E1 from V1 to V2. Just representing this path with E1 makes everything confused. Okay, this is confusing. Just marking E1 for that makes everything confused. The reason for that is you don't know whether you are moving from V1 to V2 that way or just V2 to V1. When you just say E1, you don't know whether you are going that way or you are coming back that way. So that is ambiguous. So in that case, you have to give the vertex too. That means rather just putting E1, you could put V1, E1, V2 if you are going that way. Or if you are coming back that way, you could just put V2, E1, V1. Okay, let me write that clearly. So what is given here is, this is ambiguous if you are going, let's say you are going that way, then you could give V1, E1, V2. If you are coming back that way, then you could give V2, E1, V1. Okay, it depends on which way you move. Just giving E1 is just making the reader confused. Okay, then go down. The notation V1, V2 in the above figure is ambiguous if used to refer to a work. It could mean V2, E2, V3 or V2, E3, V3. Okay, let me explain that. Now let's talk about V2 and V3. You have V2 here, V3 there. There are two edges between these two vertices. Okay. Let's say you just wrote, and there's another thing. Here's the loop. Let me put the loop to this loop. Okay, what this says, E2, what this says. Let's say you just put v2 v3 as the path, v2 here and v3. Okay, but it's confusing, right? Why you don't know whether you are going that way or this way. Okay, so it is again confusing. Because of that reason, you have to include the edge, whether you are going through edge 2 or edge 3. All right, so if you are going upward, you could go upward like this, or you could go through the downward edge. Right, so let me mark that. The upward case is this upward path. So this is the downward path. Okay, and then again the notation v1, v2, v2, v3 in the above figure refers to unambiguously to the walk v1, e1, v2, e2, v3, e3, v3. Let me show that. So it is v1 right here, v2, and then it says v2 again. I'm talking about that. It says v1, v2, we go to v2, and then again it says v2. That means you are going in the loop, and then it says v3. Okay, that is same as this notation. That means v1 across v1, you are starting from v1, across e1 you go to v2, and across v2 e2 you come back to v2, across e3 you go to v3. All right, so both notations are same in that case. They are same. Okay, so go down. And there's another example. This is a very good example. This explains everything to you. In the graph below, determine which of the following are walks, trails, paths, circuit, or simple circuit. So you have to recognize which one is which. All right. So there's the graph given to you, and there are walks given to you. There are 5 walks. Okay, let's work one by one. All right, so the first case, give me a second. In the first case, V1 right here and E1 like that, V2, E3, all right, and then V3, E4, V3, E5, V4. All right, so this is what is given to you. Right, so it has repeated vertices. No repeated edges. All right. So what this would be: has repeated edges, no repeated has repeated vertices, no repeated edges. There's another thing: start and end are different, and ends are different. Okay, so something like this is called a trail. This is a trail. Okay, it has only repeated vertices. Go back to the definition. Trail. So this is a trail. Yeah, right here. It do not have repeated edges, but it can have repeated vertices. Starting and end allowed at the same. It's starting and end at the same point is allowed, but it is not necessary. Okay, so go back to that example. So this is a trail. Okay, only vertices are repeating. Now go to the next case. It is E1. That means you go through that edge, and then E3 that edge, and E5 that edge, and then after E5 again E5. That means you are coming back on the same edge, and then E6, and then going down. Okay, this has repeated edges, repeated vertices. Has repeated edges, and start and end are different. Okay, so this is a walk. Okay, this is not a trail. This is not a trail. This is not a path. This is a walk actually. Let me use a different color. This is a walk. Okay, so go to the next case. It is V2, V3, V4, V5, V3, V6, and then V2. Okay, this has repeated vertices but no repeated edges. Has repeated vertices, no repeated edges. Start and end are same. Sorry. All right. So this is actually a circuit, right? Let's go to the definition of a circuit. Circuit, which is right here. A closed walk contained at least one edge that had more than one edge. It's closed, okay, and does not contain a repeated edge. Repeating edges are not allowed in circuits. Okay, I'm reading this. In circuits, repeating edges are not allowed. Closed is a closed walk, contains at least one edge. All right, so let's go back. It's a circuit. So this is a circuit. Just go to the next problem. V2 to V3, V3 to V4, V4 to V5, V5 to V6, V6 to V2. Alright, this is again very interesting. This has no repeated edges, no repeated vertices except the starting and ending point. Sorry. No repeated vertices. No repeated edges. Let me put except the start and end. Let me copy this one about also. I think I have to mention this, otherwise students might be confused. Copy. Give me a second. Okay, let me write it. Except the start and the end. All right, good. All right, so this is this does not have repeated vertices, no repeated edges, so that is a simple circuit. Okay, it's a simple circuit. And then go to the last two parts. It is V1, E1, V2, E1, again coming back to the same place. All right, so starting from V1, E1, V2, again coming back to the same place. All right, so this is, let me write with descriptions. It has repeated vertices and it has repeated edges. Okay. It has, actually it doesn't have repeated vertices except the start and the end. Has no repeated vertices. All right, has no repeated vertices. Inside brackets I have to put that except the start and the end. Okay, and it has repeated edges. And the other thing is start and end at the same place. Start and end are same. Actually here also I have to write it. start and end are same. All right. Okay, so this is a closed walk. Okay, this is a closed walk because it start and end at the same place. It has only repeated edges. Okay, this is a closed walk. All right. In the last case, it is just one vertex. You are not going anywhere. Okay, you are just staying at the same place. So this is a trivial walk. Okay, you could say it's a trivial walk if you need. All right, so we discussed this example. This example had a lot of different problems. It had 6 different problems. So you could understand all the concepts. What are the paths? What are the trails? What are the walks and circuits, simple circuits, trivial walks, and everything. All right. So let's go to the next section. This section is about subgraphs. First of all, I will give you the definition of a subgraph. A graph H is said to be a subgraph of graph G if and only if every vertex in H is also a vertex in G, every edge in H is also an edge in G, right? Okay. And every edge in H has the same endpoints as it has in G. Alright, so these are the subgraphs. Actually, the concept of subgraph is very easy. So the concept goes like this. Let's say you are given a graph. Here it is denoted as G. So you take a part of that graph. You take a part of that, not the entire. Maybe entire thing is also subgraph, even though it is equal to the subgraph, the entire graph. A subgraph is some collection of vertices and edges. You could choose the way you want. Okay, you could choose the way you want. It's a collection of vertices and edges. So I'm going to explain this example. You can understand it very well. List all subgraphs of the graph G with vertex set v1 and v2. These are the vertices v1 and v2, and edge set e1, e2, e3, where the endpoints of e1 are v1 and v2. That's clear. Endpoints of e1 are v1 and v2, and endpoints of v2 e2 are v1 and v2 again, and ends of e3 is a loop at v1. Okay, so this explains the end of each ends of each edge. There are 3 edges, so each edge should have 2 ends. All right, so go down. I don't know whether you thought about this early. This simple graph has 11 subgraphs. 11 subgraphs. That means you take one part at a time. Okay, so let's say in the first case, let's say you get only one vertex. Okay, you get that vertex only. So actually that makes a graph. That's a singleton graph, just the vertex. You take this vertex here. So that also makes a graph. So there are 2 graphs now. Now you take this vertex and that vertex. So that makes a graph. Right? Now you take this vertex, that vertex, and this edge, like this. So it is a subgraph. This vertex, that edge, it's a subgraph. And then you take this vertex along with that edge, this vertex along with that edge. That's a subgraph. Okay, like that you can consider all the combinations, all the possible combinations, by taking edges and vertices. All right, so you could write all the 11 subgraphs. So if you just keep your eye on last subgraph, this is same as the given graph. Same as the given graph. Okay, that is same as the given graph. Alright, so this is all about subgraphs, and that is the end of today's class. So from next day I will start the second part of this section. Second part is also very simple like this, so you will be able to understand. Thank you very much.